Hi there, and welcome to this walkthrough of GCSE or a GCSE light topic. So this might not cover everything in a GCSE course. It's mainly geared towards the IGCSE. It doesn't cover lenses and things like that, for instance. Okay, but most of the content is fine for GCSE and IGCSE. So first of all, we're going to look at the first phenomenon is reflection. So you've got a picture there of, I think it's Cape Town. You can see a very nice reflection on the water, very still water. And let's get into the law of reflection then. So the main law of reflection is the angle of incidence I is equal to the angle of reflection. And the main issue here to get across is, or the main thing is that you need to draw a normal line, and the angles are with reference to that normal line. The normal line is a 90-degree line, 90 degrees to the surface that the rays are incident on. Okay. Now, if students weren't told that, they might measure the angle between the mirror itself and the ray, which wouldn't be correct. And the reason why we're fussy about that is if you look in the bottom right there, if you have a in the first case, that's what the case similar to the case that we've got already displayed above it. But then if you look at the other two, concave and convex surfaces, it would be very difficult to work out the angle to the surface of the mirror if it was curved. Okay, so regardless of the geometry of the surface, if you draw a normal line, then you will measure the same angle. Okay, so all three of those angle of incidences are the same because they're measured from the same reference point. Okay, so hopefully that explains why we have this normal line, and usually it's dotted, the normal line drawn, as I said, with a protractor 90 degrees to the surface. Now, I've just got a little note there. In some books, it's hardly any books in Britain, to be honest, and more books from overseas. In some books, an additional law of reflection is stated, which says that the incident ray, the reflected ray, and the normal to the surface of the mirror all lie in the same plane. Well, that's a given pretty much in every situation I've ever seen in a school exam question, okay, in Britain. But just in case you ever come across that, I mean, there is, as far as I'm concerned, really just one law. That would be more of a condition of the law, of the main law, really, rather than, to me anyway, rather than another law in itself. But I wouldn't worry too much about that. That's just semantics, really. Okay. So then we get into refraction, and this is where most questions would come up, because there's only so much they can ask in exam questions about reflection, really. You could talk about reflection, about how we can see why, if this didn't work, then we wouldn't be able to see our reflections clearly. And you could talk about glitter balls and things like that, where you can't see. They're not, because of all the surfaces are all at different angles to each other. But refraction is the sort of major part of this topic at IGCSE anyway. Loads of different examples you can bring in about refraction, how things look as though they might be bent or broken in the case of that spoon. And there's a really good PhET simulation about refraction as well. If you type in PhET refraction on Google, you'll find it. You can change, you can have like multiple rays and things like that. You can change different blocks, and it's really good. It works all the time, which is great, like all those simulations on PhET. You can change the block to be a semicircular block and things like that as well. Really good. So what is refraction then? So refraction occurs when a wave changes speed as it goes from one region to another. And in almost every case, it will also change direction as well. The only time it wouldn't change direction is if it was incident along the line of the normal, okay, which we'll come on to later on. Then it wouldn't change direction, but it would change speed, okay? And you can't see the change in speed on a diagram, but you could see the direction change, which, as I said, happens in pretty much every case. Water waves slow down as they pass from deeper to shallower regions, and you get the ripple tank out. There's various types of ripple tank. You can get really expensive deluxe versions, but I've used all the different variations, micro versions and things like that. And I do struggle myself to get that to work sometimes properly. There's a lot of degrees of freedom in setting up a ripple tank. So it needs to be done well in advance of the lesson, I'd say, to get it, make sure that it's working 100%. Sometimes you have to put surfactant on the water and things like that, and make sure the dipper's at exactly the right height. Quite fussy. There are some simulations. I think you can get this to kind of work on a PhET simulation as well, but I haven't found an ideal simulation yet for it because, as I said in the past, I've struggled with the ripple tank. And light slows down as it passes from air into glass, perspex, or water, or pretty much anything else that you're going to come across in school physics. And it's always air into something or something into air in all the problems at GCSE anyway. Okay. Oh, and you've got the wavefronts there shown. Students would have been introduced to this in a previous PowerPoint. So you've got wavefronts here, and you can see that the distance between two wavefronts is the wavelength, so the wavelength's getting smaller there. Okay. So let's have a look at the rules for refraction in terms of diagrams. So when light refracts from air into something else, so from air into glass or air into water or anything like that, then it's going from a lower refractive index to a higher refractive index. Or at this stage, because we haven't introduced the concept of refractive index yet, we could just say from less optically dense to more optically dense. And light would bend towards the normal. So the angle of refraction's got to be less than the angle of incidence. It's got to be bending towards the normal. It's got to be obvious to the examiner that it is. So you have to be careful drawing this. Always draw it in pencil and making sure that it's obvious, clear that these angles are not almost the same or anything. You try and maybe accentuate it so that you can see that the incident angle is larger than the refracted angle when you're going from air to glass or air to water or anything like that. Okay, so I'm not that fond of the term optically dense because I think students quite often forget the word optically or optical, and then, density. Optically dense and dense are not the same thing, and I think it's better long term to talk about refractive index. The refractive index of air, we'll find out, is pretty much 1, and the refractive index of glass and other materials is going to be 1 point something, so larger than 1, 1.3, 1.5 in the case of some materials, some mediums, or in the case of diamond, it could be 2 or something like that, or above 2. Right, so that's going, most cases in exam questions would be going from the light going from air into another medium. So air is a medium, glass is a medium, and as it goes from one medium to another, it's crossing a boundary there. Okay, so there's quite a lot of language depending on the exam board to get familiar with there. But then we do sometimes cover questions where it goes all the way through and then out the other end. So we have to have a look at going from more optically dense to less optically dense, or a higher refractive index to a lower refractive index. And the rule there is that it will bend away from the normal. So the angle of refraction's got to be noticeably greater than the angle of incidence when you're drawing it. Always make sure you've got arrows on these diagrams. I should have said that right from the start as well. I think that's everything there. And it's worth noting, I can't show it on both slides, but the incoming, if this was the other end here, the light that was coming in here, this ray is parallel to the exit ray here, because they both started off in air. I mean, if this whole thing here was the water container, then if I follow that back down here, it might have hit here. But this ray here would be parallel with that ray. Okay. So you could talk about why pools appear shallow, or people look funny when they're sort of half their body's in the pool. They might look quite shorter. And let me finish this diagram. So you've got there where the checkerboard image there would be where the observer thinks the object is at a shallower depth. So if you ever found yourself on a desert island and you were spearfishing, then if you could see a fish, then I would probably aim between you and where you think the fish is, because if you just aim at where you think the fish is, then you're going to miss all the time, unless the fish happened to move in that direction after you'd startled it. So in terms of completing the rays here, look, this has got a complete sort of object here, so you can see it refracts towards a normal and then away from the normal. Now, students often find that hard to follow. You should really put the normals on there, and especially on the where it comes out, students are not quite sure what to do there. But what I was trying to show you earlier was that and they should really show arrows all throughout maybe. So this line is parallel with that line. And then you've got a trapezium type shape here. And again, students sometimes think, oh, well, how is that happening? How do we know how much it's bending? We might not know exactly how much it's bending, but students are used to seeing this kind of image where the interface is straight down, okay, but this one's at an angle. So what you've got to do is get the protractor, and the normal will be like that, because the normal's got to be at right angles. And once you've drawn the normal in, it makes sense. These diagrams don't make much sense to students without the normals drawn. Just remember the normal's at right angles to the surface or the interface, the boundary. So be around there, okay, there. And the same here. That's why we know it will go roughly in that direction, because the normal would be 90 degrees would be like that, something like that. And then we've got a triangular prism here, and you can see it refracts there like so. Again, much more clear with the normals, otherwise it just looks like you're making it up really. The bottom right hand side looks a little bit like a lens, like an eye lens, okay, or something like that. And you can take that quite far if you want to, okay, that analogy. But you can see there's a focus point there where all three of those rays have joined on together. You can get some really good diode lasers now with multiple rays, which are really good to use in class. So the refraction equation, and this is an equation that lots of students struggle with, particularly if they do it quite young, year 9 or 10. So when light ray goes from one medium to another, then this equation works. Now this is a kind of a special case of something called Snell's law, named after Snellius. Now there should really be another n here, really, and there should be subscripts on the n. At A level there would be. It's just that all of the cases, I think, at GCSE, well, certainly at IGCSE, maybe I shouldn't speak for GCSE because I'm not teaching that at the moment, but you don't tend to have, one of the mediums is definitely going to be air, and air has got an n of 1, and so there would just be another n in there, it would be 1. So we simplify this and just say, if it's going from air or into air, then we can use this equation, where the n is the refractive index of the medium that isn't air, essentially, okay? So when light goes from one medium to another, n equals sine I over sine r, where I and r stand for what they usually do, and n is a constant number called the refractive index. It's not, it's a ratio. It's not so it doesn't have a unit. Okay, it's just a number. So really important things. Refractive index used in loads of different spheres. And the main mistake here when students work things out with refractive index is that GCSE is that they forget to put the sign in, so they might end up they might even write the equation out, n equals sine I over sine r, and then they'll just work out n equals I over r, which isn't correct, although sometimes it actually gives you an answer that's fairly close, but that's neither here nor there. So the refractive index, really important optical property. And then you do an experiment. There's a really good video by Helen Rogerson. I'll try and put it in the sort of comment or details section. It's on YouTube, where she goes through how to do this experiment in a nice, neat, precise, quick, simple way. So I'm not going to go over that in too much detail here, but it's a really good video, and says things like making sure you don't have to draw all the way around the block, because if you're fussy about drawing the corners, you could easily nudge the block and then it puts the whole thing out then. So in terms of the procedure for this experiment, you set up the experiment there. I would prefer using perspex blocks than glass blocks, because I find that unless it's complete dark and a very strong beam, you can't see the light in the glass block. But with perspex, you tend to be able to see it even when it's not complete darkness, with a kind of average beam. So you have a ray box there. You might have a laser diode ray box, or it could just be light from a bulb with a ray box as well. So you set up the diagram there, and you do measure I and R at the way you've set it up there, using a normal. You don't have to measure it going out. You could, it depends what you're doing really, but you could just measure the incidence angle and the refracted angle, and then you could change the angle of the ray box to the glass block or the perspex block, and then do it again, and you get pairs of readings of I and R. So you're trying to get quite a large range of values of I and R, and then you can calculate an average value. And you do that from a graph. So students sometimes ask, well, why are we bothering to draw a graph? Couldn't we just do it once and work out n? Well, we might have made some mistake there, and it's better to draw a graph then, and reduce the effect of any errors that you might have had then. So the graph would be a graph of sine I against sine R, and the gradient of that graph then would be n, and that's a common thing in exam questions then. Just make sure that your calculator's in degrees, not radians for this at GCSE. You can tell because it'll have a D or deg or R or rad at the top, and depending on the calculator, there's fairly simple clicks to change the settings. You can have either degrees, radians, or grad as another setting as well. but I've never used that one. I've only ever used radians and degrees. So there's a question here then, and they can be quite demanding, these questions, I find, involving, because students might not have had that much familiarity with sines, coses and tans, trigonometry, so to take it quite slow here, really. There's also opportunities for maths errors here. Probably better to use brackets all the time in these kind of problems, or maybe not even doing it all on the calculator at once, just to reduce the chance of making a calculator or maths error. Now, working out the refractive index in a question like that's the simplest type of question, working out n, because n is already the subject of that equation. Now, working out r is the hardest there. Okay, so to work out r in that equation is by far the hardest thing. Maybe second only to working with the specific heat capacity equation at GCSE. I think those two are probably the most complicated things to deal with, I think. But so you can see in that question, it's not that difficult, that question, to work out. But working out r, you'd have to try and make sine r the subject, and then you've got to use sine to the -1 then, which again, students might not be that familiar with. At IGCSE, it doesn't often come up that they got to work out r. Working out I, again, isn't that trivial, again, because you still got to use inverse sine as well. Worth modeling that heavily to show how you do that, what calculator buttons you got to press, you got to use the shift function and things like that. And it's doable though, but it's something to return to at the end of year 10 and year 11 in the run up to the final exams. Now, I put a little slide here on dispersion. This isn't part of a course that I teach at the moment, but it's something just, not just teaching to pass the course. It used to be in courses a while ago, and it might still be in some GCSE courses. So dispersion is occurring when white light is split up by a prism into its constituent colours there. Used to be asked in Oxford entrance exams, I remember, long ago, multiple choice question. I remember once they said, what do they call this? And one of the choices was refraction, and it is due to refraction, so I think it was a bit of a difficult question there. But they wanted the term dispersion, but not likely to come up in most current courses, I don't think. But you could see the different colours refract by different amounts. Now, total internal reflection is the second big sort of topic at IGCSE anyway. Total internal reflection has got loads of uses and is really important. So, what is it? So it occurs when light is incident on a boundary between more optically dense to less optically dense, so higher refractive index to lower refractive index, and that's crucial. It can't work from air into glass. It's got to be, say, glass to air, okay, or water to air or something like that. And the angle of incidence has got to be greater than a critical angle, which is specific to the material, the medium. So this is conceptually, again, quite difficult, I think, this. And there are some problems, I think, with the theory or the way this is taught still a little bit, which I'll try and flag up now in a second. So and it depends how far you want to take these things. Sometimes there are faint rays that some teachers ignore, or some courses ignore. Others, maybe at a higher level, maybe you do need to think about these things a little bit more. But let's have a look. What have we got here? This particular thing here talks about this partial reflection there, okay? But most courses, if you go in below the critical angle, then the light will refract out. Okay, so you could kind of ignore the dotted line going up the top right there. And so the critical angle is this larger angle here. That's what it's trying to show you. And then we're going to change the angle and see what happens. So an angle less than the critical angle, it will refract out. And it's going from more optically dense to less. So it refracts away from the normal. So we're using the refraction conditions there. So this partial reflection, I think most people could ignore that, really, okay? And then if you go at the critical angle, so the angle of incidence has been changed, maybe you've moved the ray box like this, and technically it's supposed to, at the critical angle, shoot down here, which you can never ever get to happen, okay? This is not a realistic thing that at the critical angle it would shoot down here. What you find is it refracts, and then it gets to a point, and then it reflects totally inside, okay? But, in books and in exam questions, if it says at the critical angle, then it will go down at 90 degrees to the normal there, okay? But I would say that's not a realistic thing, to be honest. Okay, and then above the critical angle, you will get total internal reflection as well. Okay, I think there's something like that on another slide here as well, or the next one, I think it is. So the critical angle is the angle of incidence in the denser medium that results in, as I said there, mathematically, an angle of refraction of 90. And the earlier equation, the sine I over sine r, if you had the full version of that equation, you could derive, at A level anyway, you can derive this equation from the other one. But because you've only got the one n and it's the wrong n in the GCSE equation, you can't. It's not that trivial. It's not really doable really to derive it properly. But these two equations are related, and the first equation does lead to the second one, really. Okay. But as I said, you can't really get that angle of refraction to be 90 degrees in reality in a real situation. C is called the critical angle there. So I have to be careful because little c stands for loads of things. Stands for speed of light, stands for critical angle here, and stands for specific heat capacity as well. So it's a bit annoying that they've got multiple things for the same, multiple uses for the same letter. So that just adds a bit of difficulty again, really there, okay? So you could see on here they've got that faint ray there reflected in the first sort of picture. And at the critical angle, as I said, allegedly it shoots down this way, which, as I said, you can't get it to do that really. It goes from this kind of situation to this at around a critical angle. And you might, students might think, well, what's the point of this? Well, it's got loads of uses in everyday life. Now, it's called total internal reflection, and if you're making notes, you can abbreviate that to TIR, but you can't abbreviate it to TIR in the exams. You need to show the examiner that you know what is meant by that. Okay, so total internal reflection, which is kind of this sort of says exactly what it is, really, doesn't it? Okay, so here's a question here. I don't know why the sign is uppercase there, but whoops, working out the critical angle. So again, this one you're going to have to be careful here working this out. You've got to use inverse sine again. Okay, so there's quite a lot of use of the inverse sine function there, sine to the -1. Modeling is the key, and just keep doing as many questions as you can on that, really. So the critical angle there is 42 degrees, and glasses could come in thousands of different types, maybe tens of thousands of different types, but most glass in exam questions comes out to be 40 odd degrees, the critical angle. So in terms of uses then, now you've got to be careful with the uses, okay? Now one use would be a prismatic periscope. You must say the word prismatic or infer or use the word prism at some point, certainly in IGCSE, because you can get mirror periscopes, okay? And you might ask yourself, well, why would you use a prism instead of a mirror? But there are reasons, which I'll come on to now. So glass and perspex both got critical angles around 42. So if you, the angles there that the light's coming in on there, maybe this would be a submarine periscope, are 45 degrees. So it's going to go through like that. I've got a little video that I've made. Maybe I'll put a link in the description to that as well on YouTube, showing me messing around with these right angle prisms and showing sort of how you can set this up, okay? The prismatic periscope and also a bicycle reflector, because they work the same way. You just got to move the prisms around a little bit. So I'll put a link to that in the description. So yes, a good use, but it's not one that I tend to ask students to remember, because if you don't remember the word prism, then they don't give you the mark in IGCSE, because of the fact that you could have a bit fussy, but you could have a mirror periscope. So yeah, that's what I've sort of emphasized here as well about a mirror periscope, because the mirror, it is a bit fussy though. I think it's maybe it's exam specific, I'm not sure. So there are advantages to using prisms rather than mirrors, and the surface of a prism doesn't deteriorate in the same way as the silver surface of a mirror, and also the image is brighter. When total internal reflection occurs, more of the light is reflected than would be the case from the surface of a mirror. And also you can get double reflections from a mirror as well, from the top surface of the mirror and the bottom surface of a mirror. So if you're trying to look for some really fine change, then that would be an effect, okay, with a mirror, which wouldn't be there for a prism. Bike reflectors come up in a lot of IGCSE type questions where the students have to fill in or draw the rest of the line, see what happens. So a bike reflector might be on the back of a bike, tends to be, as opposed to a lamp on the front, made up of many small perspex prisms arranged like that. So there's normally two bits of perspex, different refractive indices. Okay, so this is the air here, and then there would be some more plastic here, but of a different refractive index. Okay, so a different material, and then there would be loads more of these prisms. Okay, so the light comes in, totally internal reflects there, and then comes back. So the reason we have these on bikes is so that cars that have a bike in front of them, they can see the bike in the dark, because hopefully the car will have its headlights on, and the headlights will reflect. The light from the headlights will reflect off the bike reflector. Really good, saves loads of lives. And you could talk about cat's eyes here, Percy Shaw, things like that. Okay, there's quite a lot of hinterland you could talk about here. So that's something I like talking about. And there's a picture of a bike reflector there, so you could see lots of prisms there. But the point is, it's not air. Sometimes some students think this bit's air here. Maybe I should really draw another plastic on here as well. But just to show there's two different materials so that you get the total internal reflection. Again, I think I'd probably not use that as my example, because again, I think some examples you have to put prismatic reflectors or mention the prism again. Now, this is what I'd say the main use of total internal reflection: optical fibers, because it's not easy to get that wrong, where it's easy to get the other ones wrong. So fiber optics or optical fibers, huge number of uses. The internet, endoscopes, loads of different things. At A level, we go into a lot more detail about the cladding and the core there, but really good to mention, and loads of examples you could do in class on optical fibers. And most departments have got equipment with optical fibers in, and there's loads of sort of uses of physics you can put that to and discuss. Now, it's always worth noting there that you'll get a refraction as the light goes in, because light is going from air maybe there to a core, which would be a different refractive index. That's more of an A-level issue, to be honest. And again, students sometimes struggle, think, well, why do I know it's that angle? Well, remember, you've got to draw that normal. So if you draw normal there, this angle is going to be the same as this angle here. And it's always worth emphasizing to students that there'll be a bit of tolerance in an exam. If they showed you this angle line coming in here and they said finish the diagram, you wouldn't have to do it exactly. There would be a slight sort of allowance for people having a slight error on measuring one or two of the angles there. Okay, so fiber optics, the uses for communication: infrared, and visible light sometimes, okay, but more often infrared. And you could talk about some courses that want teachers to teach about comparing fiber optic communication with standard microwave and radio waves, things like that. Okay, depends what course you're teaching, really. Okay, endoscope is a really good use to talk about. So for investigating inside the body without cutting people open. So putting the endoscope either through the mouth or up the anus, depending on what part of the body you're looking at. Really important use of total internal reflection. Now, finally here, I've got a little bit about diffraction. This isn't in the IGCSE course anymore. It used to be. Diffraction occurs when light spreads out after passing through a gap or round an obstacle, a sharp corner, that kind of thing. You can see there's some diffraction of C waves, for instance. That's more an A-level thing, but I thought I'd stick it in because you're not just teaching to pass the test. Okay, diffraction. And diffraction becomes significant when the size of the gap, if you're talking about a gap, is comparable to the wavelength of the wave. So you've got the wave fronts there, and you won't get much diffraction in the first case there, but you will get significant diffraction in the second case because the gap is about the same as the wavelength. And that's about it. Okay, that's the IGCSE sort of using light covered then. Now we've got a final slide here, which I got from a website, which will remain nameless. And I think I put it up on the screen once, and a student put their hand up and said, "Sir, I think there's a mistake there." Yeah, see if you can spot the mistake there. I'll just there's quite a bad mistake there in this diagram. I quite like this bit here showing the multiple reflections. I think that's what caught my eye first, but the mistake isn't there. Okay, see if you can spot the mistake. Okay, and I think I'll leave it at there.